Okay, so good morning once again, and we shall start with the lecture. See that we are talking about photoelectric effect and dual nature of matter and radiation. In that, we are studying now, as we have studied photoelectric effect, we will be now studying the de Broglie hypothesis. Okay, so let's have a quick revision. Photon we were talking about. Okay, so photon was defined or given birth by Leonard and Einstein, as we had talked about. Now see that this photon travels in a straight line. We know this, its momentum is P equal to E upon C. And all these things we have talked about earlier. So I'm quickly going to the photoelectric effect. Okay, the de Broglie hypothesis. Applications we have seen last time. And now let us start to study dual nature of radiation and matter. Okay. Now see that wave theory of electromagnetic radiations explained the phenomena such as interference, diffraction, and polarization. On the other hand, quantum theory of electromagnetic radiation successfully explained the photoelectric effect, Compton effect, black body radiations, and X-ray spectra. Means wherever there was emission-based phenomena, we know that light acted or electromagnetic radiations acted as particle nature. And wherein there was a wave phenomenon like interference, diffraction, or polarization, there it acted as the wave nature. So we then believe that radiations have dual nature, that is wave and particle nature. Now Louis de Broglie suggested that the particles like electrons, protons, neutrons, etc. have also dual nature. That means they all act sometimes as photons and sometimes as wave. That is, they also can have particle as well as wave nature. Now, see that in no experiment matter exists both as a particle and as a wave simultaneously. Means, if you take a coin and if you just toss it, then we know that only one side will be there appearing on the at the top or towards our or ahead of us or in front of us, and that side is either it may be heads or it may be tails. But it will never happen that heads and tails will be both together. Such was the condition that in no experiment or in any experiment, matter will exist in the form of a wave or in the form of a particle. It will not behave as a wave and as a particle in the same experiment. Remember this. So it is either the one or the other aspect. That is, the two aspects are complementary to each other. They are not supplementary, remember. They are complementing each other. Now his suggestion was based on a very practical suggestion was there, very natural suggestion was there. See that first is the nature loves symmetry. See, our body itself is having symmetry. Every particular thing. That's why the concept of center of mass, center of gravity came into existence, right? So about that, symmetrically all the things are there. So symmetry, nature loves symmetry. The universe is made of particles and radiations, and both entities must be symmetrical, right? Now, de Broglie wave. See what he assumed. According to de Broglie, a moving material particle can be associated with a wave. A moving material particle can be associated with a wave. Followed. That is, a wave can guide the motion of the particle. Followed. So a particle can follow such behavior. So we may say that this is a matter wave. It's a particle wave or matter wave, right? So the waves associated with the moving material particles are known as de Broglie waves or matter waves. Followed. See that he assumed a very nice thing. Actually, see that Einstein had developed theory of relativity at that time. And what Einstein believed is a highly energetic particle moving with the speed of light, okay, it can turn it into energy. It will be transformed into energy. So what does it mean? It means highly with a particle moving with very high speed, right? It will turn itself into radiation. Energy is energy radiations, isn't it? Means a particle can transform itself into a wave, right? And we know that electromagnetic radiation has wave nature, isn't it? So the origin of his hypothesis, de Broglie's hypothesis, lies in two persons' discoveries. First is Max Planck's, who believed that energy can be quantized, so E is equal to h nu. And second, Einstein's theory of relativity and this particular relation E is equal to h nu. Both together, they were the basis of de Broglie's hypothesis. So, according to de Broglie, a moving material particle can be associated with a wave. That is, a wave can guide the motion of the particle. Thus, the waves associated with the moving material particle are known as de Broglie waves or matter waves. Now, expression for de Broglie wave. See that this is particularly is the de Broglie wave. It has a particle which is moving like a wave now. So, a wave is associated with a particle. So, this is lambda, the wavelength. Now, see this. According to quantum theory, the energy of photon is E is equal to h nu. This is not V, this is nu. Okay, h nu, which is equal to hc upon lambda. Nu is equal to c upon lambda. So, according to Einstein's theory, energy of the photon was E equal to m into c square. Then, lambda is equal to h upon m into c. Right? We have substituted for E. Now, lambda is equal to h upon p. Right? Or lambda is equal to h upon p, where p is m into c, which is mass of the particle, and c is the velocity of the particle, is the momentum of a photon, right? Now the particle has energy with it, so it is a photon. Now, if instead of a photon, we have a material particle of mass m, these were the things which were proved, right? For photon, these were the things proved by the photoelectric effect itself. Now, what de Broglie did is he just transformed these things for simple matter particles which are energetic. Remember, highly moving particles, such as electrons, such as protons, all these particles. So, material particle of mass m moving with velocity v. Then the equation becomes lambda is equal to h upon mv. So, this was the momentum of the photon, and now we come back to our matter particle. So it is the momentum of the matter particle, which is m into v. This particle is the expression for the de Broglie wavelength. This is the wavelength associated with the matter particle. So lambda is equal to h upon mv, right? Now see that de Broglie wavelength is inversely proportional to the velocity of the particle, right? The faster the particle is moving, naturally the smaller will be its wavelength. If the particle moves faster, then the wavelength will be smaller and vice versa. Now, if the particle is at rest, then the de Broglie wavelength is infinite. Such a wave cannot be visualized, remember. Because the de Broglie wavelength, he himself told that when the particle is in motion, then only this wave will be present with the particle. So, if the particle is at rest, then we can't deny that wave is not possible. What we have, or then what de Broglie had suggested is the de Broglie wavelength is infinite, right? And therefore it is hard to visualize. See the thing, he can't say that for particle at rest, wavelength is impossible or the wave is impossible. This was not his prediction. What he told is wavelength may be there, but it will be infinite, and so it will be hard to visualize. Followed? So de Broglie wavelength is inversely proportional to the mass of the particle, and the wavelength associated with a heavier particle is no doubt smaller than that with a lighter particle. So obvious, because it is a matter wave. See that all the properties of matter will be possessed by this de Broglie wave. So if the heavy particle is there, naturally the wavelength will be slow, or the wavelength will be less. No doubt velocity will also be small. So in that particular fashion, Using the rules of mechanics, we can visualize this. So de Broglie wavelength is independent of the charge of the particle, right? De Broglie wavelength is independent of the charge of the particle since it believes or it behaves as a matter particle only. So whatever may be the charge, the wave will be associated with it. Now matter waves like electromagnetic waves can travel in vacuum and hence they are not mechanical waves. Matter waves are not electromagnetic waves, but they are not produced by accelerated charge. Remember, matter waves are not electromagnetic waves because they are not produced by accelerated charges. Remember, simple moving particle can produce matter wave. So it need not have that much acceleration with it, right? So matter waves are probability waves. Remember, this is the probability, amplitude of which gives the probability of existence of the particle at that point. Very nice concept. Get the understanding very clearly. Okay. Matter waves are probability waves, right? So it's the probability that matter will have a wave associated with it. Okay. And how to see whether it particularly has that wavelength with it or not, or wave with it or not, is the amplitude of which, that is the amplitude of this wave. If it is high, naturally our probability is also high. So we believe that this particular matter particle will have wave with it. Okay. Now let's come to the experiment of Davison and Germer. A beam of electrons emitted by the electron gun. Now see the arrangement. It's the electron gun over here. Is meant to fall on a nickel crystal. So this is a nickel crystal. Cut along cubical axis at a particular angle. So this will be the axis cut according to our requirements. The scattered beam of electrons is received by the detector. So this is a detector which can be rotated at any angle. So it can be rotated like this. It can be rotated around its own axis also. The energy of the incident beam of electrons can be varied. Varied means here changed. Huh? The energy of the incident beam of electrons can be changed by changing the applied voltage of the electron gun. So this electron gun has given such voltage. This voltage is, see that this has a voltage changing arrangement or voltage divider arrangement. We say voltage variable arrangements, variable voltage we are giving. So if you vary the voltage of this particular filament itself or electron gun itself, this voltage will be also electrons which are incident on the crystal will also be of different voltages, different energies. Now, intensity of scattered beam of electrons is found to be maximum when angle of scattering is 50 degree and the accelerating potential is 54 volts. So, when this potential was 54 volts and when this angle phi was say 50 degree, then at this particular, now this angle, yeah, angle phi was 50 degree. So for these both things, these electrons, they found to be with maximum intensity of scattered beam of electrons is found to be maximum. So this is maximum intensity. So maximum intensity means maximum number of electrons as we know. So theta plus 50 degree plus theta itself. See this theta plus 50 plus theta. Since it is a it's a straight angle, right? Along the axis. So it is straight angle. That is theta is equal to 65 degree. So the angle with the crystal itself should be 65 degree. So for nickel crystal, lattice spacing, whereas the lattice spacing is small d, which is 0.91 angstrom unit. For first principal maximum, that is n is equal to 1, electron diffraction is similar to X-ray diffraction. So we know that as the beam of electrons is there, this will be giving diffraction since it is the beam which is emitted. So see that this behaves as a matter wave. We know that diffraction is a wave phenomenon. So electron diffraction also takes place, and this is similar to X-ray diffraction. Therefore, Bragg's equation, which was used earlier It is 2d sine theta equal to n lambda. This gives lambda is equal to theta. We can substitute n we can have as 1 since this was the principal point. This was first diffraction. So this is lambda is equal to 1.65 angstrom unit. Okay, first order diffraction we can find out. So we are able to find out, see the wavelength of this this emitted electron beam or electron wave, which is lambda is equal to 1.65 angstrom unit. So see how small this wave is. Just imagine 1.65 angstrom unit means 1.65 into 10 raised to minus 10 meter. I hope you understand. See that there are some graphs with us. What happens if we change the intensity of scattered beam and intensity of the beam? So this is the intensity of scattered beam at 44 volts, and this is the incident beam. Let's see the structure. This is that 48 volt. So we can see that this intensity is also increased. And now see what happens at 54 volt. At 54 volt, whereas phi is 50 degree, this intensity happened to be maximum. See this. So after this maximum intensity, it is not increasing. That's why it is maximum. So now it is again reverting. See this. Okay. So like this, you get the curve. So this is according to the German and Davison experiment. They found out that at these two particular things, this particular maximum intensity can be found out. And now say that at 64 volt means even after this, when you increase the accelerating potential, see that this particular thing happens like this. Okay, so intensity of the beam is happen to be like the initial ones. Therefore, de Broglie wavelength of moving electron at V equal to 54 volt is 1.67 angstrom unit, which is in close agreement with 1.65 angstrom unit, which was happened to be seen or the observed things and the calculated things. They were quite in agreement with each other, and therefore de Broglie's hypothesis was accepted with a great honor and great respect. Okay. Now, therefore, lambda is equal to h upon square root 2m e into v. All these things we have studied earlier. So lambda is equal to 12.27 angstrom unit upon square root of V. If you have some values of this H and M in and E for electrons, then you can come up with this particular relation. Now, intensity versus anode potential, that also we can find out like this. Okay, now diffraction pattern after 100 electrons. See this. After 3000 electrons and after 70,000 electrons. See, you can clearly see these bands. Okay. So this is about the de Broglie hypothesis. Now just look at the page number 317 of our book. 317 of our book. Just have a look to that. Wherein we have written these equations for de Broglie wave. Now see that this lambda is equal to h upon m into v. Now this h upon this about this v velocity of this particle, we can write down one particular expression which was given to us by the simple kinetic energy equation, which is the equation written on page number 317. It is Ek, which is equal to half mv square. So from that you can have V is equal to square root 2 into Ke, or rather 2 into Ek upon m. So if we substitute that over here and rearrange the terms, you will get the last equation which we talked about just now. This particular thing. Okay, so lambda is equal to h upon 2m into Ev. Now this Ev is nothing but the kinetic energy. So kinetic energy, as we have done in photon in photoelectric effect, it is nothing but E into V, right? So this 2m into E into V can be found out with that particular expression. The expression on page number 317. Okay, so I hope you enjoyed this particular lecture and these particular things. Okay, see that diffraction results or this refraction experiment is also given in the yellow box of our textbook on page number 319. So have a look to that. It's quite close to this particular Davison and Germer experiment. Okay, graphite crystal is used, a thin sheet of graphite is used over there. Electron beam is there. Electron is made incident by the hot cathode, and then this particular electron beam is incident on this graphite target, and it gave us the diffraction images or diffraction rings on the screen. This evacuated bulb is taken, or evacuated discharge tube we may say is there, and like X-ray diffraction pattern, you have seen the diffraction pattern due to this particular graphite electrons also. So just have a look into that particular diagram in our textbook, which is on page number 319. Okay. So by this, dual particle or duality of matter is also believed. And thus, nowadays we believe that matter as well as energy both have dual nature of dual nature. Okay. So electromagnetic radiations and matter both are having waves with them, also particle nature with them. Okay. So with this, I'm stopping with the screen sharing. Now let's stop for a minute or for say 5 minutes, and let me know if any doubts, if anything is not understood, let me know. Yes. Is there anything which you want me to explain again or to throw light on? Yes. Else we may see one or two same experiments which are based on this X-ray diffraction or animation of Davison and German experiment. If you could give me 2 minutes, I can search that. Shall I? Shall I search? Okay, okay. Let me search. Till that, you go through that yellow box on 319 page. 319 page gives you the experiment of diffraction. Do read it right now. Okay, see that as they have mentioned about the X-ray diffraction, we'll see that there is X-ray diffraction. Just have a look. Are you able to listen to what they are saying? Yes or no? No. Okay, okay. I'll just stop sharing. I'll just share it again. Just a second. Now, are you able to listen to it? Good. So, understood this, beta? Liked it? Yes or no? So always see that whenever you have some such references in your textbook, do go to that those references and have these things done. Means have these things known at least. So nice, isn't it? So love liked it. Yes, I personally liked it very nice. It's very much rather. So remember always, as this technology is there developed for you, always use it constructively. Always whenever you have such references, do have do have the complete explanation of these things, because our textbook is that way limited. Everything cannot be incorporated in our textbook, but such references, when we are talking about Bragg's law or like X-ray diffraction, you must know what is that. Okay, so such small videos, I have shown you video of just 4 minutes. Such small videos are possible. Do use them. Do get the understanding with the help of them. Okay, so we shall stop here and keep studying. All the best. Take very good care of yourself and your family. So, bye for now.